Hello everyone, my name is Shivam Soni. We are from School of Electrical Science of Indian Institute of Technology Bhubaneswar from India. We are very thankful to ICDIPC for giving us opportunity to represent our research work, which is entitled as Automatic Audio Event Recognition Schemes for Context-Aware Audio Computing Device. The authors are Shivam Soni, Sudipta and M. Sabarimalai Manikandan. These are my presentation outline. First, we will discuss the introduction of the research work, followed by motivation and major objective. Then we will discuss briefly about the literature survey which is related to our work. Then we will discuss the methodology, followed by result and conclusion. In real life scenario, there are multiple sound events simultaneously occur. For example, a busy road in rush hour. The events may include traffic noise, people talking, etc. The human brains are amazingly good at distinguish these sounds. But as of yet, there is not any machine that can detect these events up to human accuracy, because the main reason is the polyphonic nature of the audio events. That is the reason this area is underdeveloped as its counterparts like speech and music recognition. Audio event recognition is defined as detection of individual sound events that are present within an audio. The system will target on a specific audio event, for example, gunshot, keyboard typing, footstep, etc. And the context awareness is the property of device that locate awareness by sensing the physical environment. Here is some potential application of audio event recognition. It is useful in surveillance application for detection of dangerous events and crime, in context awareness for autonomous core purpose, in monitoring for recognition of noise sources and machine fault, in multimedia indexing and retrieval, in assistive technology. It is also helpful in urban planning for the analysis of human and animal activity, and biology for the recognition of species and analysis of biodiversity. Now we will talk about the motivation behind this work. As sound contain lots of information about our everyday environments that can be used for extracting portion of the events, which is helpful in many practical applications. Besides, in some cases, surveillance via video camera is inappropriate. For example, camera-based indoor robot navigation. A little loss of sight would cause serious problem. So the next is the deep learning based neural network, which is especially designed for object recognition, can be successfully used to recognize the environmental sounds. The major objective of this research work is to create a huge database of 7 class sound, including aircraft, construction, music, nature, speech, train and vehicles, to explore an effective machine learning and deep learning based AER scheme using MFCC feature for audio surveillance application, to identify the optimal audio frame size for yielding better recognition accuracy, to develop cloud based AER framework for remote audio sensing and monitoring services, and studying the real time feasibility of AER framework on Raspberry Pi computing platform. In literature, we studied that the performance of audio event recognition system mainly depends on selection of audio features and classifier. Here is the audio features from different domains which are used in literature for audio event recognition application, like from temporal domain audio features, spectral domain, cepstral domain, time frequency domain and statistical features. Here is the different classifier which are used for speech and non-speech classifications. Here are the summary of the literature survey related to our research work. Here is the overview of implemented system. Here we created large-scale audio database for training and testing purpose. In this work, we used MFCC feature to represent audio and 3 classifiers such as SVM, support vector machine, fully connected feed-forward neural network, and 1D convolution neural network to detect 7 class audio events. The performance of all 3 AER schemes are evaluated under different audio frame size such as 100 millisecond, 250 and 500 millisecond. The details of used database in this research were summarized in this table. We used recording instrument like H1 handy recorder, EVI, STR digital recorder and mobile handset for recording audio under different environmental conditions. We also collected audio from the public multimedia website like YouTube, freesound.org and GTGen library. The total duration of audio database is about 81 hours. In this work, to investigate the performance of 3 machine learning classifier, we used a standard MFCC feature which is most commonly used in many environment, speech and music sound classification because this feature is inspired from human auditory system. Here is the generalized block diagram of extracting MFCC feature. In this work, as first scheme, we select conventional machine learning classifier multi-class support vector machine for detection of audio events. It is supervised classification algorithm. As it is multi-class problem, we used one versus rest SVM approach with RBF kernel. The specification of multi-class SVM based AER scheme is shown in the table. The major limitation we found that the computational complexity is more in this scheme. As second scheme, we selected fully connected feed-forward neural network with 3 layers. The architecture of network is shown in this figure. It takes MFCC feature as an input and produce the detected class as output. The specification of fully connected feed-forward neural network based AER scheme is shown in this table. As third scheme, we select 1D convolution neural network. The proposed model consists of 4 convolution, 1 max pooling layer, 2 dropout layer, 1 flattened layer and 2 fully connected layer. The detailed architecture of network is shown in this figure. It takes MFCC feature as input and produce the detected class as output. The specification of 1D convolution neural network based AER scheme is shown in the table. All classifier model has been trained with MFCC feature of about 1 million audio frame using 5-fold cross validation. Each model is tested with 11991 frames of each class. The confusion matrix for 3 AER scheme is shown in the following table. The performance of audio event recognition scheme are evaluated by using benchmark metrics such as precision, sensitivity, which are also known as recall, and F1 score. The result shows that the 250 millisecond is the optimal frame length for all the 3 schemes, and 1D CNN with 96.34% F1 score outperform feed-forward neural network with 95.72% and multi-class SVM with 85.84%. So the conclusion is, in this work we presented 3 audio event recognition scheme using MFCC feature for recognizing 7 sound classes. All 3 audio event recognition scheme were evaluated using wide variety of audio signal in real time using our audio event monitoring GUI. In this work, 1D CNN scheme with 96.3% F1 score outperform other schemes for audio frame length of 250 milliseconds. The recognition rate of aircraft train and vehicle class sound with more than 90% accuracy are the state of art of our work. The results demonstrated that the significance of selection of frame length for achieving better recognition performance. Currently, we are trying to implement the 1D CNN based audio event recognition scheme on Raspberry Pi computing platform. This is the developed offline graphical user interface for audio event testing where we can upload our audio file, we can choose the sampling frequency and the model scheme from which we want to test, and we can select the frame size. Then we can see the event detection result by pressing import model, process, predict and result button respectively. We can also see the training curve, loss curve and confusion matrix plot by pressing show button. This is the cloud-based audio event recognition framework where it will start detecting audio event after pressing the mic button attached to left corner. These are the references of our work. Finally, I am very thankful to Indian Institute of Technology Bhubaneswar for supporting us. I am thankful to Ministry of Electronics and Information Technology, Government of India for funding this project, and we are also thankful to Mr. Sudipta and Mr. Manikandan for helping in preparation of video presentation.